Today we study ESA25H, a second look at Galileo's law of inertia. We have shown that the shortest path connecting two points A and B in a three-dimensional Euclidean space is nothing but a straight line. And the proof involved a new mathematical technique called calculus of variation, developed by Euler and Lagrange. And this method is a very interesting method and a general method to verify that the minimum function that minimize a function that minimize a functional is a function of a function. In Newton's second law, we remember Newton's second law, F equals ma. Net external force applied to an object of mass m experiences the acceleration x double dot in an inertial frame of reference. A special case is called the free particle motion. Free particle and means force, net external force is zero. If force is zero, then mass times acceleration is a zero vector. Because any object in classical mechanics is massive, we should find later that the rest mass of a particle called a photon, the light quantum, is actually massless. But we do not consider the relativistic case in this case. So in classical mechanics, mass is a positive definite. There's no object of mass zero. So we can divide both sides by the mass m to find that the acceleration is a zero vector. It is trivial to find the integral, definite integral, from a t time equals 0 to a certain time t. The result is to 0 to t dt prime x double dot t prime. I use t prime because it is integrated over an interval from 0 to t. This is a second order derivative. Therefore, the result is the difference of the first order derivative, but at both endpoints. So x dot t subtracted by x dot evaluated at t equals 0. So from this, we find that velocity of a particle at time t is velocity of the particle at t equals 0 plus the definite integral. By the way, the acceleration is nothing but 0. So this integrand is from 0 to t, this integrand is exactly a zero vector. Therefore, the velocity of the particle at time t is identical to the velocity of the particle at t equals 0. This is true for any t. Therefore, we can say the velocity of the particle is a constant vector. We call this is a free particle that is free of acceleration. Free of acceleration is identical to the fact that velocity is uniform. It doesn't change at all depending on time. We can carry out the definite integral from 0 to t one more time to find the difference in the position. The difference in the position is called the displacement. Displacement is minus 0 is by definition integral of derivative of x of t prime. So if I carry out the definite integral of this is nothing but without this derivative, so nothing but the position at time t subtracted by the position vector evaluated at t equals 0. This is called the displacement of the particle from during the time interval 0 to t. All right. However, now we can find that velocity of the particle is not 0 anymore. It is the acceleration of the particle is exactly 0 for a free particle. However, the velocity is a uniform. It is a constant. Because it is a constant, this integrand can be factored out of the integral. Therefore, the integral is x dot 0 vector multiplied by a trivial definite integral evaluated from 0 to t about dt prime. This is nothing but t minus 1 at 0, so that is t. So position of the particle is the position of the particle at t equals 0 plus the uniform velocity evaluated at any time. For convenience, I have chosen the t equals 0 multiplied by time interval. This elapsed time is t, so vt. So displacement of the particle is not uniform, but it changes with the same rate along xyz axis in a uniform way. All right, let's consider the motion of a free particle whose velocity is the same. In classical mechanics, the mass of the particle is also uniform. It does not. It is invariant. It does not change at all depending on any condition, as long as the system is closed. In relativity, the mass can change depending on the velocity, but let's forget about that. We restrict ourselves to the Newtonian classical mechanics. We define the linear momentum. Linear momentum is P written in we denote the linear momentum by vector P, and that is defined by the product of the mass and the velocity of the particle. Because the velocity of the particle, of a free particle, is a constant vector, we don't care about the time dependence. It is independent of time. Therefore, the linear momentum evaluated at time t is identical to the linear momentum evaluated at t equals 0. We recall that the force is mass times acceleration. Mass times acceleration, the double time derivative, and mass is independent of time in Newtonian classical mechanics. I can pull this first order derivative out. Then I find it is the first order derivative of a product mass times velocity. This is the linear momentum we just have defined. So time derivative of the linear momentum is nothing but the mass times acceleration. But wait, we are considering the free particle whose acceleration is identical to a 0 vector. Therefore, the force is 0 and time derivative of the linear momentum is also 0. we introduce an arbitrary variation from the straight path connecting two fixed points A and B. Why? We are considering a free particle. The velocity of a free particle is a constant. The velocity of the free particle is a constant of time. Therefore, the position of the particle is 0 plus a velocity that is a constant vector multiplied by time. What's that? Depending on time, the path is a straight line. So x component is x dot t, y component is y dot t, and z component is z dot t, and x dot, y dot, z dot are the Cartesian components of the velocity of that particle. Therefore, we can consider the variation of the particle's path. We know A and B are two positions, the initial and final position of this particle at time ta and at time tb. And we know the actual physical path of the particle from A to B is a straight line. Why? Because of the law of inertia. The free particle does not have any acceleration, and the uniform velocity guarantees that the path of the particle, the path of the free particle that starts from A and arrives at B is a straight line. Now, let us make use of a similar method. What does it mean by? What does it mean by? Is there any further abstract meaning that is equivalent to the law of inertia? All right. We would like to find another path that is not physical. The physical path connecting the initial and final positions is just a straight line. But we introduce unphysical paths, keeping the two endpoints the same as the physical path. So this is x of t, a vector depending on time, that whose time interval is from ta to tb. And this, wait a second, x of t is a red one, and this is x of t plus delta xt. We include the unphysical variation from the physical path that is in red. So this amount of the shift from the straight path is now understood to be the delta x vector. That is the variation from the physical path. All right. Now we have mass times acceleration equals 0. Whatever displacement, the variation from a physical path, we have this delta x is non-zero except for the two endpoints. However, the law of physics called the law of inertia states that mass times acceleration is always a zero vector. If I multiply a scalar product with the variation vector delta x to this equation, the final result is right-hand side is absolutely zero, and left-hand side is force scalar product with the variation from a physical path. We know this is exactly zero, whatever variation you may bring in. Therefore, we go one more step. Let's go further. just make use of the Leibniz rule for the derivative of a product function. Okay, this is similarly to the Leibniz rule. Derivative of product is derivative, and their sum. Something like that. I have x acceleration and x variation. So why don't we rewrite this one in terms this. So dt, linear momentum, and velocity, scalar product of variation. If I take the derivative, it's acceleration, scalar product of variation, plus mass velocity dot scalar product variation of this velocity. Okay. This is what we had. So this left-hand side can always be expressed in terms of the time derivative of this scalar product, linear momentum, and the variation, and subtracted by this one. By moving the second term to the left-hand side, we find that mass times the velocity, scalar product with the variation of the velocity. All right, we have arrived from the law of inertia. We have arrived that this is identical to the law of inertia. And delta x is an arbitrary variation from the physical path that is the straight line connecting A and B that are the starting and end point of the physical path of a massive particle that is free of any net external force. Now we can integrate this equation from the physical time interval that we are interested in. We evaluate the definite interval from Ta to Tb. By the way, because this first term, when it becomes an integrand over the time interval, this derivative disappears, and what we find is the difference of this value inside the brackets evaluated at the endpoints. What's that? The result is scalar product with the mass times velocity. We don't know. The velocity is just a constant vector. It does not have to be zero. However, this variation vector evaluated at both endpoints are always a zero. Therefore, this scalar product, both of them are zero. 0 minus 0 is a 0. As a result, our equation of motion for a free particle that is nothing but the law of inertia, the velocity is constant, can be expressed as an integral, and this integral is always a 0. Always a 0. What's that? We are familiar with this kind of expression. Leibniz told us AB prime equals A prime B plus AB prime. What about A squared? AA prime, because A prime A plus AA prime, that is a 2AA prime. Just like that, this prime is nothing but the derivative. It can be generalized to the case of the variation of the path. The variation of the path for 1/2 x dot squared should be this. Have multiplicity factor of 2. Finally, we can rewrite this integral to be this, neglecting the term of order delta square or higher. What's that? We are familiar with the fact that this 1/2 mass times the velocity squared, this is nothing but the kinetic energy, capital T. We arrive at the point that law of inertia, that is acceleration is zero, is equivalent to the fact to order delta, the kinetic energy of the time integral of the kinetic energy over a time integral where the integration, the domain starts from the starting point to end point. That is zero. The variation of the time integral of the kinetic energy is zero. What's that? It is an extremum, either the maximum value or minimum value. Either maximum or minimum. Only if it is the case, this variation should be zero at order delta. Now, we are ready to define the action as, that's the reason why we have been using a strange notation. S is called action, and this is, in general, it is to be generalized to the Lagrangian, named after Lagrange. And Lagrangian, in this case, that free particle is nothing but the kinetic energy. In general, Lagrangian, we shall find that Lagrangian is kinetic energy subtracted by the potential energy V. But this free particle does not have functional dependence in the potential energy. Potential energy of a free particle is nothing but a constant, so we forget about the potential energy in this case. So action for a free particle is nothing but the time integral of the Lagrangian, and Lagrangian is identical to the kinetic energy. We finally arrived at a variation of the action. Action is time integral of Lagrangian. Lagrangian is kinetic energy for a free particle. And this variation is a zero. This variation is a zero. Why? We just have found. Then, what about the order delta square contribution of the variation of the action for a free particle? We can find the explicit variation of the kinetic energy by varying x by delta x. Finally, this variation of the integrand, that is called the Lagrangian, has the leading contribution cancel, and we have factor 2, multiplicity factor in the expansion of this, and order delta square contribution. What we have found just previously is this integral vanishes when the variation is given from the path x that is a physical, and that is the straight line for the case of a free particle. Therefore, this is a zero. And then, what's that? We have a variation of the action for a free particle. The first order vanishes because it is either maximum or minimum. Or the second contribution, delta square contribution, shows that it is explicitly positive definite. As a result, we have found that action, that is the kinetic energy, in general should be subtracted by the potential energy. However, in the case of a free particle that is free of a potential energy, whose potential energy is constant, action is the time integral of kinetic energy only. And if it is the case, action of a free particle becomes minimum on the straight path that satisfies the law of inertia, whose the particle's velocity is a constant vector. That's it for today. Thank you for listening.